Okay, so it's Monday or Tuesday, May 19th. And we're here to talk about oxidation reduction reactions for the general chemistry class at Northern New Mexico College. Okay, so last class, we kind of wet our beak a little bit with, we learned how to assign oxidation states, and we had an introduction into balancing oxidation reduction reactions in neutral media. All right, so we'll do a few more of those today. We only had a chance to do 3 or 4 of those last class. We'll do a few more of those today. All right, and then we'll step into balancing oxidation reduction reactions in acidic media. All right, and to balance oxidation reduction reactions in acidic media, you first have to know how to balance oxidation reduction reactions in neutral media. And then after we learn how to do them in acidic media, then we'll take a final step into balancing oxidation reduction reactions in basic media. And to balance them in basic media, you first have to know how to balance them in acidic media. And again, to balance them in acidic media, you first have to know how to balance them in neutral media. So we're just going to be kind of building upon what we've learned. All right, so let me just go to my little database here of reactions, and we'll pull some up. All right, so let's look at some okay, so let's take a look at all right, and we'll give you a minute to copy that down. Okay. I still have my. All right. Again, first step is to assign oxidation states to all of the atoms. Okay, so here we're going to have +1. This is going to be -1. We know hydrogens are +1. We know oxygen is -2. We know sodium is +1, oxygen is -2, and hydrogen is +1. And here we have pure elements, and we know in pure elements the oxidation numbers are 0 in all pure elements. Okay, so now that we have done that, again, all right, for those of you that weren't here last class, that is the most important thing, is getting the correct oxidation numbers. If those are wrong, everything after it is guaranteed to be wrong. Everything. All right, so you really got to learn how to apply those rules that I passed out last class. Okay? All right, so let's take a look. Whose oxidation number is being reduced? In other words, getting smaller. Well, let's see. I'm seeing hydrogen starting out at +1 and ending up at 0 there. Notice some of the hydrogens stayed the same. Some of the hydrogens stayed the same. I don't think we saw this in any of our examples last week. But this hydrogen has been reduced. So we can write the reduced atom is hydrogen. Okay, its initial oxidation number is +1. Final oxidation number is 0. We'll worry about the reducing agent later. Okay, the oxidized atom, well, let's see, whose oxidation state is getting bigger? Looks like chlorine. Starts out at -1 and ends up at 0. I can write chlorine there. Initial oxidation number -1, final oxidation number is 0. So now we're prepared to fill in the oxidizing and the reducing agents. So the oxidizing agent causes our chlorine atom to be reduced. So we're looking for a reactant chemical that contains the atom that is itself reduced. In other words, contains hydrogen. So H2O is our oxidizing agent. Notice the oxidizing agent must contain an atom that is itself reduced, in this case, hydrogen. Similarly, the reducing agent must contain an atom that is itself oxidized. So we're looking for a reactant that contains a chlorine atom. So here it is, sodium chloride. That is our reducing agent. Okay, everybody with us? All right, I'm going to erase these guys here while you're filling in the rest of that table on the small board. Okay. All right, does everybody have this now? All right, we're still going to need this. So we're going to write down here our half reactions. And we'll write down oxidation, and down here our reduction. All right. So let's see here. We'll draw a line across here. And the oxidized atom is chlorine, which starts out at -1. And it's going to end up at 0, which means it must have lost an electron. Remember, the charges must balance here. It is an equation after all, right? It's a half equation, half reaction, right? Similarly, we have for a reduced half reaction, we have hydrogen beginning at +1. It's going to end up at 0, which means we must have added a negatively charged electron. So we have charge of 0 here, a charge of 0 here. Okay? Now, so we're kind of balanced. Remember, the key here, once you have your initial half reactions written, the key is to get the number of electrons the same. All right, the number of electrons released by the oxidized species must equal the number of electrons gained by the reduced chemical species. We're already at that point here, right? We have 1 electron here and 1 electron here, so we're good. But that's not good enough. That's the first thing we should check. We should also check that the number of chlorines that are being oxidized here equals the number of chlorines being oxidized in our given equation. And that's clearly not the case. Here I have 2 chlorines that went from, that doesn't much look like a Cl there. Okay, here I have 1 chlorine, but here I have 2, right? This is the only chlorine here. So both of these chlorines that end up as 0 must have come from the sodium chloride. So I must multiply this half reaction by 2. I must multiply it by 2. All right? Now, if I'm going to multiply that reaction by 2, I have to multiply this reaction by 2. Right? So let's proceed to do that. Right? And when I expand this out, all right, there we go. There we go. Okay, so we should be able to go ahead and balance here. All right, so let's see. I'm going to use red for that. So here's my 2 chlorines. All right, so I need 2 chlorines here. I need 2 chlorines there. Now, if I look at the hydrogens that are being reduced, well, there's 2 of them being reduced there. Right, there's 2 of them being reduced here. Now I have 2 here, but remember, we said not all of these hydrogens are reduced because the ones that go to form the sodium hydroxide, the oxidation number of hydrogen there stays the same. So what we should do here first is, okay, I have 2 sodiums here. I'm going to need 2 sodiums here. All right, I need 2 sodiums there. Okay, now we can take a look. Well, I have 2 oxygens here. I better have 2 oxygens here. All right, let's just write that a little clearer. I should have left some space to write coefficients. Okay, now, seemingly we're done here, but we should stop and check, especially since this was a situation where we had an atom, an element, hydrogen, where some atoms were being reduced and some weren't. So we should stop and check and make sure everything is okay here. Here I have two sodiums, two chlorines, two chlorines, right? Two oxygens, two oxygens. Now I should have four hydrogens, but only half of them should be reduced. Only two of them should be reduced. So here's the two that are being reduced. Here's the other two that are not being reduced. Okay, so we're done. This is good. This is good. The number of electrons transferred during this chemical reaction is 2. 2 electrons. And again, the number of electrons in the oxidation half reaction must equal the number of electrons in the reduction half reaction. The other thing to always check is that the number of atoms that are being oxidized in your half reaction must equal the number of oxidized atoms up here. Same with the reduction half reaction. Okay, again, I want to point out, this is the first time we've seen an example like this, where some of the atoms are being reduced and some are not. You have to account for those, right? You have to account for those. Okay, any questions or comments? Any questions or comments? All right, we'll move on to another one now. All right, I'm only going to do maybe one more of these, and then we'll move on to the acid and the acidic and the basic, because you have to be able to do this to do those. So it's not like we won't see this again. All right, so let's look at let's find a good one here. Okay, let's try this one. So we have this powerful, is it oxidizing or reducing agent? I can't remember. This is very, very toxic, very highly reactive. Nice black powder. Manganese chloride plus Cl2 plus water. Okay. And while you're writing that down, I'm going to start assigning oxidation numbers here. Okay. Now, I've written in the oxidation numbers for everything but the manganese. Okay? We know this is a neutral chemical compound. The sum of the oxidation numbers must equal the charge on the compound. So here I have two oxygens that are both -2. The manganese must be +4. The manganese must be +4. Similarly over here, I see chlorine. Oh, sorry. It should be -1 on chlorine. And then I have 2 of them, which add up to the -2. Okay, I was jumping the gun there a little bit. All right, so same situation here though. Neutral compound, sum of the oxidation numbers must equal 0. All right, so I have -2 here, so this manganese must be +2. Right, so we can see it's the manganese being reduced. And let's see, the chlorine is going from -1 to -1 there, but it's going from -1 to 0 there. So this is a similar situation like the last problem, where we had some of the atoms of one of the elements being involved in the oxidation reduction process, and some of those atoms were not. Right? So in this case, it's going to be the chlorine atoms. So let's take a look. We'll fill in our little table here. It's always good to fill out something like this. You'll see, I think I forgot to ship you the assignment. Okay, but we'll have them ready this time. Okay, so the let's look for the reduced atom. I always like to look for the reduced atom first, because reduced, whose oxidation number is being reduced? In other words, getting smaller. If you're being reduced, you're getting smaller. So it's the manganese going from +4 to +2. So manganese, okay? And its initial oxidation number is +4, and its final oxidation number is +2. We'll worry about the agent later. The oxidized atom is the chlorine. The chlorine, it's going from -1 to 0. Okay, now to get the oxidizing agent, I'm looking for the chemical that contains the reduced atom on the reactant side. That's MnO2. Right, MnO2. And the reducing agent, I'm looking on the reactant side for the chemical that contains the oxidized atom, which is HCl. HCl. Okay? All right. Now that we have that, I'm going to erase these charges up here. There's not charges, but oxidation numbers. They're not always the same thing. Quite often they are, but they're not always. Okay, so we'll draw our little line here, and we'll put oxidation and reduction down here. Okay, and I'm going to take this away. Well, we still need it. All right, so for the oxidation half reaction, it's the chlorine going from -1 to 0, and it's releasing an electron. For the reduction half reaction, it's the manganese starting out at +4, and it's ending up at +2. So I have to add 2 electrons to reduce it from +4 to +2. We're going to add 2 electrons there, right? Add 2 electrons. Okay. Now, I have 1 electron in the oxidation half reaction and 2 in the reduction half reaction. That means I have to multiply this reaction times 2, right? That reaction times 2. And I'm going to expand that out. Okay, and we see 2 electrons there, 2 electrons there, right? So the electrons balance. Okay, now let's see here. It looks like we're going to be okay. I have 1 manganese here, 1 there, and 1 here. Here I have 2 chlorides being being oxidized, and I have 2 here in the half reaction being oxidized. So that's kind of tells me, okay, it's time to go start putting in the coefficients. So 1 manganese, 1 manganese, all right? 2 chlorines here, 2 chlorines here, all right? So I'm going to need to put a 2 here, except I also have these 2 other ones that are not being oxidized. I have 2 chlorines here being oxidized, but 2 more here not being oxidized. That means I need 4 of them on the reactant side. 2 are being oxidized and 2 are not being oxidized. Okay, is everybody clear on that? You have to understand that. That's a very important point, right? 2 are being oxidized and 2 are not. So I have to have the total number over here. Okay, and the manganese, I only need 1. Now let's look at everything else. Let's see, I have 2 oxygens here. I only have 1 there, so I'm going to need to put a 2 here. All right, put a 2 there. And let's see, we're probably good, but we've done all this work. Let's go back and check. 1 manganese, 1 manganese. 2 oxygens, 2 oxygens. 4 hydrogens, 2 times 2 is 4 hydrogens. 4 chlorines, 2 here that stay the same, and 2 here that are oxidized. So we're done. We're done with this. Okay? And how many electrons are transferred during this chemical reaction? 2. 2. All right? So for every mole of chlorine gas that we produce, there's going to be 2 moles of electrons that are transferred. Okay? Any questions or comments here? Any questions or comments? Okay, so now that we're all experts on how to balance these reactions in neutral media, we're going to jump into balancing reactions in acidic media. Okay, so let's take a look at one here. Now I'm going to have to write this reaction kind of small. Hopefully you'll be able to see it. Okay, so I have okay. So let's start assigning oxidation numbers. Everybody can see that?
Yeah, I can.
Okay. So here we have -1. Here we have -2, -2, and +3. Okay. Now, I have -2 3 times here. All the oxidation numbers added together got to equal -1. So the iodine is +5. The iodine is +5. Similarly here, I have -2 7 times. So what number plus 7 times -2 equals -2? All right, so this is -14, or 2x, 2 chromiums there. So 2x equals +12, or x equals +6. So the chromiums are +6 each. Each chromium is +6. Okay? So we can get out our little board here. Okay? And we're going to write in here. Let's see, who's being reduced? Whose oxidation number is getting smaller? Looks to me like the chromium, going from +6 to +3. So here we'll write chromium, starts out at 6+, ends up at 3+. All right? As always, we'll worry about the reducing agent later. Now, whose oxidation number is getting bigger? Well, let's see. The iodine starts out at -1 and ends up at +5. So that looks like iodine to me. Starts out at -1, ends up at +5. All right, ends up at +5. Okay, so the oxidizing agent. I'm looking for a chemical species on the reactant side that contains the atom that is itself reduced. So that's going to be dichromate. Cr2O7, don't forget the charge. All right? For the reducing agent, I'm looking for the chemical on the reactant side that contains the atom that is itself being oxidized. So it's going to be I-. Okay? All right. Everybody good here? Everybody good? All right. Now pay attention to this one. This is the first one.
The bottom of the board's been cut off for this.
Raymond,
Yes.
I'm having really bad connection, so.
Yeah, I hear that going in and out. Just try the best you can. If you lose us completely, I am recording it. I'll put it on YouTube later.
Okay.
Okay. But try to follow along as best you can. Okay.
Okay.
So you can see the bottom of the board here now?
Yes.
Okay. Now, we're going to put our oxidation half reaction and our reduction half reaction. Okay. Can I take the small board away now? Hello? All right, I'm going to take it away.
Yes.
Okay. Now, we said that the iodine was our oxidized atom, starting out at -1 and ending up at +5. Right? So that's a difference of 6 electrons. 6 electrons. You got to get that right. Okay? Reduction half reaction, we said that was the chromium going from +6 to +3. So chromium starting out at +6, ending up at +3. So that's a difference of 3 electrons. A difference of 3 electrons. Okay? Now, let's see here. 6 electrons, 3 electrons. So I got to multiply this half reaction by 2. Multiply it by 2. Right? So 2 chromiums plus 6 electrons gives me 2 trivalent chromiums. This is a pretty toxic ion right here. You've been reading the paper that's here in Los Alamos. There's the aquifer is being contaminated by hexavalent chromium ion. Okay, so let's take a look here. All right, well, I have 2 chromiums here and I have 2 there. So that's looking kind of good. It means I'm probably going to put a 2 here. Let's go ahead and do it. Let's go ahead and do it. All right, and I have 1 iodide here, 1 iodine here, 1 iodine there. We're looking pretty good. Anybody see a problem though? There's 2 major problems in this overall reaction up here. 2 major problems. 2 major problems. Nobody sees it. How many oxygens are on the reactant side? Come on, how many?
7.
Sorry, didn't hear you.
7.
How many are on the product side?
3.
3.
3. Right, so that's a major problem. In addition, let's look at the total charge on the reactant side. I have -1 here and -2 here, so that's -3 on the reactant side. The total charge on the product side is +6 here. I have 2 chromiums at +3, so that's +6, and -1 is +5. The charges are not the same. Electrical charge has to be conserved in every chemical reaction. Okay, electric charge must be conserved in every chemical reaction or every chemical equation, right? And it is not. Now, how are we going to balance that? All right, well, this reaction is being done in acidic media. In acidic media. So I'm going to add 8 H plus cations over here. All right, 8 H plus cations. Okay, -3 plus 8 now gives me +5. The charge is balanced on both sides. The charge is balanced on both sides. Okay, now I have a problem. We took care of one problem, but we introduced another one. Because now I have hydrogens here. I don't have any hydrogens over there. I have 8 hydrogens here, and let's see. I'm going to get rid of this charge business here because we already took care of it. Let's look at number of oxygens. We said we had 7 oxygens here and 3 there. I need to add 4 more oxygens on that side. And I need to add 8 hydrogens on that side. 8 hydrogens and 4 oxygens sounds like 4 water molecules to me. 8 hydrogens and 4 oxygens. Okay? So there we go. There's our balanced overall chemical equation in acidic media. But again, we've done all this work. Let's go back and double check it. Make sure everything is correct. Here I have 8 hydrogens. There I have 8 hydrogens. 1 iodine, 1 iodine. 2 chromiums, 2 chromiums. 7 waters. All right, 7 waters. Well, I have 7 oxygens. 7 oxygens. 3 oxygens there, 4 oxygens there is 7. So that's correct. We should check and make sure on our oxidized and reduced atoms. I have 1 oxidized iodine, 1 oxidized iodine, 2 reduced chromiums, 2 reduced chromiums. And the last thing, always check this, even though we did just check it. Check it again. Check that the charge is balanced. So here I have 8 positives and 1 negative, so that's positive 7, and negative 2 is positive 5, right? I have 3 negatives and 8 positives, positive 5. Here I have 6 positives and 1 negative, is positive 5. We're done. We're done. The charges balance, and everything else balances also. So you see, in the trial and error method, there's no way you could have balanced this without having the 8 protons here, or a proton and a water molecule given to you in the starting reaction. There's no way you can balance that, all right, by that trial and error method. But with this oxidation reduction method, the half reaction method that we're using leads directly to the final answer. All right? We didn't notice, we didn't even have all the reactants in the original problem. We didn't even have all the products in the original problem. But we very easily were able to balance this. How many electrons are transferred during this reaction? 6. 6 electrons are transferred. Any questions or comments? Come on, this is your first acid reaction you've seen. You got a question, speak up. All right, we're all good? Okay, let's take a look at, here's a good one. Here's a good one. All right, let's take a look at this one. Okay, I'm going to start writing oxidation numbers in. Okay, we just saw in the last problem in dichromate that the chromiums are +6 here, right? At -14 here, +12 here adds up to -2. Okay, now we got to be careful here. This is hydrogen peroxide. You got to be very careful here. Now, let's make the mistake. Let's go ahead and make the mistake. We'll say that the oxygens are both -2 and the hydrogens are both +1. That doesn't add up to 0. That does not add up to 0 here. That tells me this cannot be 2 oxides. That tells me that this, what we're looking at is in fact 1 peroxide, not 2 oxides. So instead of being -2 and -2, it's going to be, as in all peroxides, -1 and -1. All right? You got to be very careful with that.
Raymond,
Yes.
is that a plus sign in between the oxygen and the chromium on the product side?
Yes. Yes, that's separating the oxygen and the chromiums. Okay. All right, let's fill in our little table here. All right. Well, let's see, whose oxidation number is being reduced? In other words, getting smaller. And it looks again like the chromium. The chromium starts out at 6+ and ends up as 3+. Okay, now let's see here. Who's being reduced? Or sorry, oxidized. Well, let's see. I have O -2 here, right? So we can say that's being oxidized. Or I have these other oxygens. It's more likely that these are the guys being oxidized. They're going from -1 to 0. -1 to 0. All right, so let's say that these are the ones being oxidized, not these. All right, because I don't see, well, we don't see any oxides or peroxides on that side. But let's take a stab at these two. So O, oxygen begins at -1, ends up at, and we'll leave the 0, ends up at 0. All right, now, the oxidizing agent contains the atom that is itself being reduced on the reactant side. So that's the dichromate ion. The dichromate ion. Okay, now, what's the reducing agent? Again, the reducing agent, I'm looking for a chemical on the reactant side that contains the element that is itself oxidized. So that's going to be the hydrogen peroxide. The hydrogen peroxide. If you know a little bit of chemistry, just like that manganese dioxide in a problem or two ago was a powerful oxidizing agent, hydrogen peroxide is a quite strong reducing agent. Okay, so we can take away our small board. Now, even if you had made the mistake, here, let's put those back up here. Suppose you had made this mistake, all right, and you just left that like that. Hopefully you would have caught it, because there would, well, actually you probably wouldn't have, because you would have just said, oh, this is going from -2 to 0. All right, so you probably wouldn't have caught it. I was going to say there would be no oxidized atom, but that's not the case. Okay, so here we're going to write oxidation and reduction. And here it's the oxidized atom oxygen, starting out at -1, going to O0 plus 1 electron. There's a difference of 1 electron there. All right. Again, the charges have to balance on both sides. All right. Now we'll put the chromium on the reduction half reaction. Okay, so we had chromium starting out at +6, ending up at +3. Right, and to get there, I have to add 3 electrons. I have to add 3 electrons. Okay, now we can immediately see that the electrons do not balance. So I'm going to multiply this times 3. All right, now they do. 3 electrons here, 3 electrons here. But there's going to be a problem here. All right, and again, pay attention here, because again, this is another little trick we haven't yet seen before. All right, here I have an odd number of electrons being oxidized, but I'm going to end up with an even number of electrons that are oxidized. Even number of electrons oxidized here, even number there. So I have to have an even number of oxygens in my oxidation half reaction. I have 3 there right now. That's not an even number. So what I'm going to need to do is multiply this times 2. If I'm going to multiply this times 2, then I have to multiply the reduction half reaction by 2. Right? I have to multiply the reduction half reaction by 2. Okay? So now let's write out our final form here. 6O minus gives me 6O0 plus 6 electrons. And down here, we're going to have 2 chromiums starting out at +6, plus 2 times 3 is 6 electrons, gives me 2 trivalent chromiums. 2 trivalent chromiums. Well, that's looking pretty good, because I got 2 chromiums here and 2 there. Right? We'll give you a chance to get that all written down. Okay, grab myself a little more water while you're doing that. Okay. So we can start filling coefficients in because the electrons are now balanced. All right, I have an even number of oxygens here, and I must have an even number of oxidized oxygens in the overall reaction. Okay, so let's take a look here. 2 chromiums here. So I can put a 2 here. Okay, let's see here. I'm going to have 6 oxygens being reduced or oxidized. So I'm going to need a 3 here and a 3 there. A 3 there. Okay. All right. Now, let's take a look. I'm going to use a different color here. I don't know if this purple will show up. Let's look at the charges. I have a total charge of -2 here. Total charge of -2. All right. Over here, I have a total charge of +6. +6. All right. So I need 8 more positives over here. If I had 8 more positives over here, then the charge will become +6. The charge will become +6. So I'm going to add 6 protons here. 6H plus. Okay, sorry, this board is so small. All right, so now I have +6 here. So the charges now balance. The charges now balance. So I'm going to get rid of this here. All right, I'm going to get rid of this. All right, it's kind of getting too busy here. All right, now let's take a look at what I have. Oh, wait a second. I said I was going to add how many? 8. 8. Why didn't somebody say that? I had to add 8 protons, not 6. That was going to give me a charge of +6 here. Okay, so now let's take a look. I have 8 hydrogens here, but none over there. None over there. And I have 6 more hydrogens here. I also have these 7 oxygens. So let's see, 8 hydrogens and 6 hydrogens there is 14 hydrogens. All right? And I have 14 hydrogens and 7 oxygens that are not accounted for on the product side. Again, that's 14 hydrogens and 7 oxygens not accounted for on the product side. 14 hydrogens and 7 oxygens add up to 7 water molecules. 7 water molecules. Okay? So that should be our final form. But as always, we're going to go back and check everything. All right, so let's see, I have 8 hydrogens here and 6 there. So that's 14. 7 times 2 is 14 hydrogens. Here I have 3 times 2 is 6 oxygens. 6 oxygens that are being oxidized. There's 6 oxygens being oxidized. Here's the 2 chromiums, the 2 chromiums. Here's the 7 oxygens that were neither oxidized or reduced. There's the 7 oxygens that were neither oxidized or reduced. So we're all good there. Let's check the charges one more time, because I almost screwed them up a moment ago. Here I have 8 positive and 2 negative, add up to +6. Here I have +3 times 2 is +6. So the charge is balanced. We are done. We are done. All right? We are done. Okay? Any questions here? If you're really interested in chemistry as a subject, you should enjoy doing these oxidation reduction reactions. Right? It's quite satisfying whenever you finish one of these. It really is an art form to balance. Well, not so much an art form as a scientific process to get them to balance. Any questions or comments here? Any questions or comments? All right, I'm
No.
going to do. Well, we're done in 15 minutes, huh? Actually, I think we'll just stick with the acidic ones today. We'll just save the basic for next time. Yeah, because we're done in 5:15 here.
You give me the rules that you gave last class for this?
I emailed them.
Oh, okay.
Emailed them before the last class. All right, let's look at. Let's see if we can find this one. Let's see, I don't know if I have any of these as. I was looking. Okay, here we go. Here we go. All right. Okay, here we go. Actually, we can't do this one. I'm looking up here and that can't be right. It cannot be right. All right, hopefully this one. Sorry about that. That couldn't have been right. In my database, I have a lot of them that I've worked out and some I haven't worked out. And I was cutting and pasting so that there's no way that what I had typed in for that last one could be correct. Okay. All right. Let's start writing some oxidation numbers. See, I don't have this one worked out, but I think we should be able to do this one. All right, so oxygen's -2. That means each of the fluorines are +1. All right, here, the iodine is -1. The fluorine is -1. Now, I have 3 iodines added together must equal -1. That means each one of them is -1/3. Remember, we saw last class, oxidation state number can be fractional, Okay? Now, we should already be able to see, at the end, I'm probably going to have a coefficient of 3 here. Notice there's an oxygen here and no oxygen over there.
Professor, real quick, I have a question.
Yeah, go ahead.
How are you getting those charges? Are those the charges on the actual ions?
That's the rules that I emailed last class.
Okay.
Okay.
I'll go take a look at them.
So for here, real quick, since you asked, a lot of times the oxidation number will just equal the charge. Okay? The oxidation numbers on a neutral molecule have to add up to 0. So if you notice here, they add up to 0. Oxygen's always -2 unless it's a peroxide like we saw in the last one. Hydrogen is always +1 unless it's in a metal hydride where it's -1.
Yeah, I remember doing those in.
I gave an assignment on that also.
Intro, you had discussed this, I think, too.
I don't remember. But I'll post a video from last class also. You'll see it worked out there. We spent about a half hour doing that last class. I know I posted a video. I must have been, I can't remember if it was this one or the introductory chemistry one. I know I posted one. I can't remember if it was ours or the introductory one. Okay, so let's take a look. Whose oxidation number is getting smaller, is being reduced? Well, that looks like the fluorine to me. Starts out at +1, ends up at -1. So fluorine starts out at -1, ends up at +1. Now, whose oxidation number is getting bigger? Well, that looks like the iodine. Right? That looks like the iodine. -1/3 is bigger than -1. So iodine is the oxidized atom, starts out at -1, ends up at -1/3. Okay, again, they can be fractional. So let's look for the oxidizing agent. The oxidizing agent is the chemical on the reactant side that contains the atom that is itself being reduced. So OF2. Okay. The reducing agent is the chemical on the reactant side that contains the atom that is itself being oxidized. That's I-. So iodide anion. Okay? Everybody has that. Okay. And again, you have to get these oxidation numbers correct. A lot of people would get confused over here. Just remember, the 3 atoms added together have to equal -1. So each one of them is -1/3. It's really not that hard. Really not that hard. Okay. So let's look at our oxidation and reduction half reactions. So oxidation and reduction. Hopefully I'll leave enough room here. All right, and we said the iodine is being oxidized. Starts out at -1, ends up at -1/3. Now, you got to get this right. The difference between -1 and -1/3 is 2/3. So 2/3 of an electron is being released. 2/3 of an electron is being released. Right? And we said the fluorine atom was being reduced. And the fluorine started out at +1, and it ended up at -1. So it must have gained 2 electrons to do that. It must have gained 2 electrons to do that. All right. All right. Hopefully this one's going to work out. I don't have it worked out in my database. Now, the first thing we have to do is get rid of that fraction there. The first thing we have to do. So to get rid of this fraction, we're going to multiply by 3. Okay, get the 3 out of the denominator. So we're going to multiply by 3. All right, so let's rewrite that out now. So 3 iodides give me 3 of these. There's our 3. All right, plus 2 electrons. Plus 2 electrons. All right. Now, let's take a look. I got 2 electrons there. I got 2 electrons there. Okay? But does anybody see a problem?
There's three iodine, right?
Well, there's 3 there. We're not putting coefficients in up here yet.
Okay.
Here, I'm going to have 2 fluorines being reduced, but I only have 1 here. I only have 1 here. So I darn well better have 2 fluorines down here being reduced, right? Because I have 2 up here that are going to be reduced. So I'm going to have to multiply this reaction times 2. And if I'm multiplying that times 2, I got to multiply this times 2. All right, I got to multiply that one times 2. Okay? Now, let's write out here our what's hopefully going to be our final form, because I don't have any more room. Two times 2 is 4 electrons. And then we'll distribute the 2 down here. Okay, give you a chance to write that out. Okay, so if I have 6 iodines being oxidized here, I better have 6 being oxidized up here, right? So I'm going to put a 6 here. And that means I need to put a 2 here, right? A 2 there. Okay. Now, I have 2 fluorines being reduced. I better have 2 up here. Well, I have 2 here, but I only have 1 there. So I'm going to put a 2 here, right? A 2 there. Okay. Now, let's see here. I have an oxygen here. I don't have any over there, but I'm not going to worry about that yet. This is in acidic media. We should worry about the charges first before we worry about the oxygens. So let's look at the charges. Well, I have -6 on this side, -6. What do I have on this side? I have -2 and -2. -4 I have on this side. -4 on that side. So I have to add 2 protons on this side, right? Notice, I'm surprised no one has asked me, how do you know which side to add the H pluses on? If I add H pluses over here, this is going to stay -6, but this is going to get bigger, right? I want to make these the same. If I'm adding positives, I have to add them to the more negative side, right? So if I add positives here, then this is going to work its way up to -4. I add positives here, there's no way I'm going to ever get that to equal -6. I'm surprised nobody asked me that. Okay, so let's take a look here. I need to add 2 H pluses on the reactant side. 2 H pluses. 2 H pluses. Okay. Now, we're almost home. I'm going to erase these charges down here just to keep everything nice and clean. All right. So let's see here. I have 2 hydrogens here, none over here. I have 1 oxygen here and none over there. 2 hydrogens and 1 oxygen sounds like 1 water molecule to me. All right, 1 water molecule. Okay, now let's go back and check everything. All right, we'll go back and check everything. 2 hydrogens, 2 hydrogens. 1 oxygen, 1 oxygen. 6 iodines, they're being oxidized. Here's the 6 iodines that were oxidized. Here's 2 fluorines that were reduced. There's 2 fluorines that were reduced. We're good there. Let's check the charges one last time, and then we're done. Here I have 2 positives and 6 negatives. 6 negatives and 2 positives add up to -4. Right here, I have 2 negatives and 2 negatives here, -4. We're done. We are done with this problem. How many electrons are transferred? 4. 4. Again, let's just go over this one last time, because we're about out of time here. The very first thing you have to do is get rid of this fraction. Get rid of that fraction. Okay? And then, again, as always, okay, we were at this step, and I saw there's 2 fluorines here that are going to be reduced. So I have to multiply this half reaction times 2. I have to multiply it times 2. Remember, the number of atoms being reduced in your half reaction must equal the number of atoms being reduced up here. Same with the oxidized atoms. Okay, I started out with just 1, but I see there's going to be 3 that are going to be reduced. Now, I didn't multiply initially by that 3 for that reason. I multiplied by that 3 to get rid of that fraction. Okay, but it just so worked out that gave me the 3 iodines that were going to ultimately end up being oxidized. Okay? Again, if you follow this systematic process, right, it will get you to the correct answer every single time, no matter how difficult the initial reaction appears to be. It will get you to the correct reaction every single time. Let's see here. Now, I know we're at the bell here. If you want to check out, I'm going to do one more here. I think this is pretty cool. I don't think I will ever give you a problem like this, but I think you should see one. And for that reason, I'm going to do it kind of quickly. But I do want to have it on the video here. Again, if you want to check out, let's stick around and we can talk about next week. I'll do this one quicker, right? Since I'm not going to give you any like this. This is what's called a disproportionation reaction. Disproportionation, right? So let's see what it is here. Now this is in neutral media. This is in neutral media. So let's take a look. So I know I'm not going to need any room to write waters or protons here. I can write a little bit bigger. Actually, maybe I can't write bigger because I need 4 products. Disproportionation reaction. So, like I said, I'll do this one kind of quickly. There's +1, -1. The oxygens are all -2. The sodiums are +1. Here, +1 on the sodium, -1 on the chlorine. So you see, Mr. T, the oxidation numbers here are the same as the charges on the ions. Here I have a pure element, which is always 0. Here I have -2 on each of the oxygens, and the hydrogens are both 1, and the oxygen is -2. So the only thing we need left to fill in are these sulfurs, right? Well, if these are -4, then this sulfur has to be +4. Has to add up to the charge on the chemical species, which is 0 for a neutral molecule. Okay, so here I have -6 and +4. -6 and +4. Or sorry, -6 and +2. -6 and +2. So that's -4 total. -4 total. So I have 2 sulfurs. So 2x plus -4 must equal a charge up here, which is 0, or 2x equals +4, or x equals +2. So each of the sulfurs is +2. They have to add up to 0. They have to add up to 0. Okay? All right. So now we have all of the oxidation states. All right? So let's go to the little board here. I'm glad I didn't have to, or that I brought this little board from school. Didn't have to rewrite it every time. All right, now, let's see. The sodiums stay the same. The oxygens all stay the same. The hydrogens stay the same. So the only thing left is the sulfur. Notice it starts out at +2. So again, as always, I like to do the reduced atom first, because I'm looking for which atom has its oxidation number being reduced, in other words, getting smaller. Here I see sulfur going from +2 to 0. So sulfur, +2 to 0, +2 to 0. Now whose oxidation number is getting bigger? Again, it's sulfur, +2 +4, +2 +4. So +2 +4. So we see sulfur is being both oxidized and reduced in this problem. We haven't seen one of these before, right? The same atom is being oxidized and reduced. Okay? So I'm going to erase all these charges here. We didn't fill in the oxidizing and reducing agents yet, but that should be quite obvious. The oxidizing agent contains the atom that is itself reduced on the reactant side, right? So that's sodium, whatever that anion is. So Na2S2O3. And that's going to be the same down here for the reducing agent. All right, so you guys can see that on the bottom there. Okay. Everybody has that. Take her away. All right. Now, the oxidation half reaction is the sulfur going from +2 to +4. Right? That's a difference of 2 electrons. The reduction half reaction is sulfur
Raymond,
going. Yes.
can you move your screen up?
Yeah, thank you. Sorry about that. Okay. The reduction half reaction, sulfur again going from +2 to 0, pure element. All right, and to do that, I have to add 2 electrons. Okay, I have to add 2 electrons. Okay, now, this is a little bit harder because it's the same atom being oxidized and reduced, but this particular one is about as easy as it gets, because let's take a look here. Here I have 1 sulfur being oxidized, there it is. Here I have 1 sulfur being reduced, there it is. All right, so I don't need to multiply these by anything. Oh, sorry. The electrons are also balanced already. They're also balanced already. So in my final half reactions, it's just going to be 1 sulfur here and 1 sulfur there. So I don't need to worry about any of that. So we should go back and let's take a look here. All right, we can balance everything else now because the sulfur is already balanced. I have 2 here, 1 of which is being reduced and the other that's being oxidized. So the sulfurs are okay. Here I have 2 sodiums. Here I only have 1, so I need a 2 here. All right, let's see. The chlorines, I have 1 there and 2 there, so I need to put a 2 here. All right, let's see. Here I have 2 hydrogens and 2 hydrogens there. Here I have 3 oxygens, none of which are being oxidized or reduced. So I better have 3 over there. There's 2 there and 1 there. We're done. We are done. Okay, we are done. Remember, this was neutral medium. Okay, neutral medium. All right, how many electrons are being transferred? 2. Right, 2. And they're being passed between sulfur atoms. Okay, again, this is called a disproportionation reaction. Right, disproportionation. Now, I have a few examples where we have multiple atoms that are being reduced. Now, we're not going to have time to do that, right? But that gets that's about as hard as it gets, right? So this is a little bit harder, same atom being oxidized and reduced. But then again, you can have multiple atoms that are either being oxidized or multiple atoms being reduced. That's a little trickier. Okay, so that's it for this. Does anybody have any questions on what we did today? All right, I'm going to stop the recording then, and then we can talk about whatever we need to talk about here.